Welcome back to Introduction to Statistics. We're going to be talking about doing hypothesis tests using confidence intervals for a population mean. Here we have all of the information we need to perform a hypothesis test using a confidence interval. Now, the thing about confidence intervals, if you remember, is that when we draw the confidence interval, we are always drawing it around a mean. So we're always marking off some area here. Okay, maybe out this far. And it is symmetric on both sides. Because of the nature of a confidence interval, we can only use it for hypothesis testing if we are doing a two-tailed test, if we are trying to find out if the mean is not equal to some value. Let's construct a 99% confidence interval to perform this hypothesis test. All right, so when we are working with confidence intervals, we do find an alpha, and we find that alpha by taking 1 and subtracting the decimal form of our confidence level. So we will get 0.01. Alpha equals 0.01 for this hypothesis test. Now we will either assume that this data comes from a population that is normally distributed, or that someone has already checked this data for us to make sure that a normal probability plot indicates normal distribution. We have to do those things because, as you can see, we have a small sample for this one. So we're just going to assume that we can use this approach. So we have alpha, but we are doing a two-tailed test, and besides, this is a confidence interval, so we actually have to find alpha divided by 2, or 0.005, tiny little area there. And we also need to find the t-value. So we are looking for the t-value, I'm going to start writing up here now, at alpha divided by 2 equals 0.005, and what is the degrees of freedom? Well, this would be degrees of freedom equal 22. So let's see if we can find that on the t-table. So there is our row 22. Let's find 0.005 in the columns. 0.005 is here. So therefore, our t-value is 2.819. But please remember, we do not go straight to the t-distribution with this value. Instead, we use this to determine the upper and lower bounds of our confidence interval. So our lower bound is equal to the mean of the sample minus the t-value we just computed times the standard deviation divided by the square root of n. And remember, for the upper bound, we just take the mean and we add the margin of error that we get by doing this multiplication. And now we can indicate our confidence interval on our distribution up here. So 99.26 or 99.3 is probably close enough there, and 110.3. So anything within there, in between the two, is within the confidence interval. Notice that we built this t-distribution around the mean of our sample, not the population mean that we are testing. So we build our confidence interval around the mean of the sample, and then, and only then, we determine if this mean is within the confidence interval. And yes, it's about right here. That would be 100. Since it is within the confidence interval, there is no reason to reject the null hypothesis. We would say there is not sufficient evidence to infer that the population mean is not equal to 100. We can also use confidence intervals when we are performing hypothesis tests to infer things about the means of two populations. So let's do that. All right, we are going to use these two samples to test whether or not the population means from which the samples were taken are equal. And we are going to do that at a 95% confidence level. Now we have to express this differently to use a confidence interval for a hypothesis test. So let's state our hypotheses first. Our null hypothesis is, as always, a statement of no change. We expect that the populations from which these samples came have the same mean. So if we subtract one from the other, we should get 0. And our alternative hypothesis is if we take that difference, it is not equal to 0, meaning the means are different. So alpha equals 1 minus 0.95 because we are doing a 95% confidence interval, and that gives us 0.05. Alpha divided by 2 because with the confidence interval it is split into two parts. We have 0, that is, there are areas on either side of the confidence interval. We will find the smaller sample and subtract 1. So we have degrees of freedom 19. So therefore the t-value at 0.025 with degrees of freedom 19 from the chart is 2.093. And here are the new equations needed for lower bound and upper bound. Instead of beginning with a single sample mean, we have the difference between the sample means. We have a t-value calculated as we have just done, and then under the square root we have the standard deviation of the first sample squared over the number in the first sample plus the standard deviation of the second sample squared divided by the number in the second sample. Now when we calculate that, that may look a little strange at first because our usual thought is compare these numbers to the means that we have, and boy, those are way off. But actually, we're looking at the difference between the means, and that should be 0. So, that's not as far from 0 as it is from 111. We are actually looking at the distribution of the mean of the first sample minus the mean of the second sample. So we need to figure out what that is. That is 7. And what is our standard error of the mean? Nope, that's not it. So there we have our distribution of the difference between the sample means. The lower bound here is at 1.18, so we're looking at somewhere in this area. And our upper bound is at 12.82, so somewhere in this area. And our confidence interval is in between those two bounds. So all of that area. And we are 95% confident that the difference between the two means is within that area. But what is our null hypothesis? Our null hypothesis is that the difference between those two means is equal to 0. Is 0 within that confidence interval? No, 0 is approximately there. So we reject the null hypothesis and we say with a 95% confidence level that the means of the populations from which these samples came are not equal. Once you get used to it, the confidence interval approach to hypothesis testing makes a whole lot of sense, but it can only be used in the case where we're looking for means that are not equal or a mean that is not equal to one other value. It's no good for a left-tailed test or a right-tailed test, only for two-tailed tests. So your classical approach and your p-value approach have wider applications. And that concludes our discussion of hypothesis testing for now.